next talk is by Aina?
Yes.
Or Aina?
Aina.
Sorry. Aina. Excellent. So you're talking about?
I'm talking about... so this is ongoing work, which is close to being done. And I'm going to talk about the implementation of a capability machine model into Iris. This is joint work so far with Alex Trygge and Lars Birkedal. So first, well, capability machines allow for very fine-grained control over pointer commissions, as we've just seen by the previous talk. And that makes them a very good target for secure compilation. In particular, we're interested in enforcing certain higher-level abstractions, such as local state encapsulation and well-bracketed control flow, that we often take for granted when we program in our high-level languages. But of course, such abstractions are not enforced at the low level, so we want to have mechanisms to do that. And also, we need tools to reason about these quite subtle properties in a language that does not enforce them. I have to say there's something missing at the bottom of the slides. I'm very sorry. My computer crashed. I'm going to keep it. Oh.
Is that Horus?
I wish. I apologize about that, but thank you for paying attention. So as I said, we need tools to reason about these quite subtle properties in a language that does not enforce them. And this is exactly what Laus Goslinsko and Dominique Debriez did in ESOP paper, where they reasoned about a machine with local capabilities. However, these tools, they're quite elaborate and complex, and they're also very long, so there's a big motivation to mechanize them. And our mechanization effort has been with the hope that we can both facilitate the process of using them and also enforce our belief that they work. So first, what are capability machines? And for that, we need to define what a capability is. So here's an image of memory. And first, a capability has a range of authority. So here, this capability lets you touch memory from B to E. Next, it actually points to an address in memory. It's here A. Note that here the address is within the range of authority, but it may very well be outside, in which case we cannot use the capability to, use A for anything, because we don't have authority over it. Then it also has a permission. So here's an example lattice. And this permission can describe how we can use the capability. In this case, the example capability has the permission read execute, which means we can read from it, and we can also execute it, which means simply jumping to it. However, if we try to use this capability to write, the program is going to crash, because we don't have write authority over it. And all of this together enforces the tagline that a capability is an unforgeable token of authority. So there is no way to expand the authority with your given capability. You can only make the authority smaller. And in a capability machine, pointers are replaced by capabilities. So how can these be used to enforce one of the properties I mentioned in the beginning, namely well-bracketed control flow? And to illustrate that, I just want to go through an example. So in this example, we rely on well-bracketed control flow to instruction at line 7. So first, 1 is pushed onto the stack. We then do a call to an unknown adversary in register R, and assert that it's still 1, so that the local state was not touched. After which we do a second, after which we push a new local state onto our stack, replacing the previous one. We do a second call, and now if well-bracketed control flow is broken and this adversary return at the first callback, then the assertion will fail, and we cannot reach the halt instruction again. So let's go through the program. Well, we push some local state. Next, we want to prepare for the adversary stack to do the adversary call. And in that case, we want to give them less authority than we have. We want to make sure they're not actually touching our local state. So we're going to make the range of our capability smaller. So in this case, the stack is represented by the read-write capability. And now hopefully they cannot touch our local stack. And then the adversary is doing some local computation, and since that program is unknown, we have no idea what they might do. So for example, in all calling conventions, we need to give the caller a return pointer, so here return capability. And in this example, the adversary decides to on the stack. So this is represented by the capability there. They then jump to the callback. So once jump to, we get back the original stack. That's our original capability. And then we pop the stack and assert that the local state does not change. Presumably we're able to prove this since they did not have capability over our local state. But then now we push the new local state, and we arrive at the second call. So we are now in this case. And again, we prepare the adversary stack. We do the same thing. We decrease the level of authority, the range of authority. But we did not, since we did not know what the adversary did and we were not careful enough, they now still have access to that previously stored capability, the previously stored return capability. And if you remember, that's exactly the capability that jumped to this point here. And since we did not remove that temporary capability in some way, they're now able to break bracket control flow. So the solution here is to use an additional tag, namely local capabilities. So here's our previous capabilities. We now have two distinctions. A capability can be local or global. And what it really means is that a local capability is the one that is representing temporary permission to do something. Temporary capability over something. But we're also going to expand the lattice. So now there are two new kinds of permissions, namely the write local ones. And it is only the write local capabilities that can be used to store locally tagged capabilities. And now we use these, this is also what Skorzenko and Divriez did, use this new kind of capability to implement a calling convention that makes sure that the adversary cannot store those temporary return capabilities that we gave them for each call. So in this case, this was the example before, and we want the adversary to lose any temporary capabilities upon return of the function call. And in this calling convention, we're going to make sure that the only capability that has write local permission is the stack capability. So or any local capability is on the stack. And then we can revoke any local capabilities by clearing the stack upon their return. So that is the calling convention that they invented. And now, well, there's a lot going on, and we want to reason about it. We want to make sure that this is capability safe, or some notion of capability safety. And, well, so far we can think a bit about what are ways that we like to reason about programs, about properties. And we like program logic, but here we want to reason about unknown codes. So if we want to reason about these semantic properties and the execution of some unknown code, a known method to do that is using logical relations. Namely, we know very well how to use logical relations to capture invariance on the type system. In this case, of course, it's an untyped language, so it's just a small variant of that is using logical relations on an untyped language to capture semantic properties of the language. And that's exactly what was done on paper. So far I really just described the setting, but I want to get into the mechanization. Before I do that, I'm still going to show a little about what the logical relation looks like on paper. And the reason for that is because I want to highlight the differences that you get when you start mechanizing that into Iris. Namely that when mechanizing it, we can give a slightly higher level of abstraction of the definitions. All right, we're going to use a stepped index cryptid logical relation. And I'm always just going to give snapshots of what it looks like through a read-write capability. So what is the validity of a read-write capability? Well, presumably the validity of a capability is going to depend on whatever that capability maps to. So we're going to use some worlds to describe some invariance over our memory. And then we might be able to say something like this, where, well, the validity of this capability means that there is a region in the world such that that region conforms to some kind of invariant that's often called a standard island, and it's with the range from B to E, because that is the range of authority of this capability. So I'm not going to show what these invariants look like, but there are some, a lot of interesting concerns here. For example, this invariant, well, we want to say that everything within the region is valid, but in that case we have already an issue, because we're defining the validity of a capability given the definition of validity. So there's a circular definition and it's not well defined. And this is what in the literature is known as the world circularity problem, and there's a lot of work that has solved this, and namely using step indexing. So, I mean, what I'm really trying to emphasize is the details sort of pile on. But then, of course, the world may also evolve. We have load and stores. So for that, we also need a future world relation. And in our case, there's something interesting. So we have these local and global capabilities. And remember, the local capabilities, the invariant should only sort of, well, we want to enforce it temporarily, and then we want to make sure that we're revoking it later. But global capabilities are really just invariant, since the global capability can be stored anywhere. So we also want a distinction between local and global capabilities, and this future world relation should model the distinction so that we can, in particular, reason about overactive control flow. All right, so on to the mechanization. It is mechanized in Iris, so just a very short Iris primer. Iris is a higher order concurrent separation logic framework. It's foundational, and it has a COC implementation, which comes equipped with an interactive proof mode. It's also a framework, which means we can embed any language into it. So the way it works is you describe the operational semantics in Iris, and from there you're actually able to prove a program logic for it. It also comes equipped with some very useful modalities. So it has invariance. It also has ghost state, which is a way of describing how your resources actually work. And then it also comes with the always and later modalities. And the key point is we can take advantage of Iris, all of these modalities, and also it's the step index model, to mechanize these cryptological relations with recursive worlds in a succinct and elegant way. So those of you that might have gone to a workshop earlier this week with Derek Dreyer could have seen this in action. But just to have an overview, typically how this is elegantly implemented in Iris, these logical relations, is by using Iris invariance for the region invariance that I described earlier in the definition. This future world relation really comes from a modality called the frame preserving update, and also a statement that's proved in Iris called world satisfaction. And what it really means is when you implement it, you don't need to describe the worlds or define the worlds. That's very nice. So those of you who have worked with step-index logical relations might know that when you define the world, you need to prove a lot of properties about it to show that it's actually well formed. But then the step indexing can also be implementing using the later modality. But what are the challenges in our particular case? So first, Iris was really designed with slightly more high-level languages in mind. So for embedding languages, it asks for both definitions of expressions, of values, of a lot of things we're used to. But at a low-level machine language, this is not always obvious. So there are some workarounds to actually embed a machine language into Iris. It also abstracts away certain details that we actually want to reason about directly. And really, in particular, there's only one frame-preserving update. And if we look up there, I mean, the frame-preserving update is the one you use for the future world relation instead of reasoning about worlds directly. However, we have the distinction between the two future world relation, which is very important to reason about well-bounded control flow. So we need to somehow pull out some of the things that Iris abstracts away to reason about it directly. So, but the roadmap for actually expressing capability safety in Iris is first to embed the language into Iris. It is then to define a program logic by proving core triples. Next, actually defining the logical relation. And here we use the Iris tools to solve the world circularity problem. Then we want to prove the fundamental theorem of logical relations. And finally, we can use the logical relation to prove examples that rely on local state encapsulation and well-bracketed control flow with calls to a non-known adversary. So in this talk, I'm only going to talk about the third point, like the definition of the logical relation. But if anyone is interested, I have bonus slides on most of all these other parts. So what are we implementing? It's this unary logical relation for reasoning about semantic properties of an untitled language. And in particular, I just want to focus on the value relation. So the same example we saw before, but on paper. So what's the signature? Well, it's an untyped language, so really the value relation is just going to go from words to Iris propositions. And typically what has been done in other implementations or mechanizations of these logical relations is to use invariants for that. So what would the validity be for this read-write capability that we saw before? Well, it's now a full range of memory, so we want to have a big separation conjunction for each address within the range from B to E. And for each of those, we want to say that there is a word such that A maps to W, that's the statement here. And this is a ghost resource, which is an Iris way of describing how your resources work in a disciplined way. And here there's some additional information, so we are also actually saying that A maps to W with permission read-write. So we also have these permissions in our ghost resources. And next, we want to say that it maps to a W, and that W is also in the validity relation. However, there is something slightly missing, and that has to do again with the distinction between local and global capabilities. So here we don't really use G for anything, but we of course want to do that because we want to reason about the distinction. So the idea is we want to make sure that local capabilities are revoked, whereas global capabilities are not. We want our model to represent that. So we're going to, that was the challenge. We want to model revocation. And we are going to do that with a collection of state transition systems, here denoted by sigma. And sigma is going to keep track of the current state of all of our locations. And those states can be either temporary, revoked, or permanent. And it is the temporary states that can then become revoked in the future world relation. Right. So here I really wanted to highlight again, the whole process of going from paper to the mechanization, and in this case, it's the world. So I mentioned this world previously, and whereas we don't have a world full of invariants in our case, this collection of state transition systems is actually also present in the world on paper, here by the state and worlds. So in the Iris mechanization, we use a collection of state transition systems, the sigma, and this is what is corresponding to the state transition systems in the world. However, all the invariants are really just described using Iris invariants. And finally, I really want to show, so there's this idea of standard islands. And in the mechanization, we now have a standard STS. And this is just describing the standard behavior of all of our memory resources. And here we're using the method of private versus public future worlds. As we can see, the revoked memory can become temporary again. And all these dotted lines means private transitions. So it's something that happens in a private future world. And in particular, it's we can privately revoke temporary memory, and they become revoked, and this is what corresponds to the stack clearing. Okay, so what's really new? So from a capability machine viewpoint, this is a mechanized formalization, and it's currently 25,000 lines of Iris code, which I highlight mostly because this does not fulfill one of the promises that I gave early in the talk, where hopefully this was a nicer definition to use than the one on paper. But I do want to say that I believe that these can be made much smaller with some clever tactical support, and that hopefully to become a more realistic use that can allow for both expanding on the definition and maybe even talk about more realistic capability machines. And the definition also comes at a higher level of abstraction. So I didn't really highlight this, but there's no step index in the actual definition anymore. We now just use the later modality and iris invariance. And then also, instead of having this world of invariance, we have a collection of state transition systems. From an iris formalization viewpoint, it is a formalization of a machine language with no distinction between program and memory, which we don't know of any other examples of so far. And we are also able to distinguish between well-bracketed and non-well-bracketed calls using public cloud conditions, which we also didn't have an example of before. So as a conclusion, this is really the first mechanization of a core model of a capability machine. So far, the mechanization includes the embedding of a capability machine language into iris, the mechanized proof of the fundamental theorem that I did not show you, but I have some bonus slides for that. And also a mechanized proof of capability safety of two non-trivial example programs, one that relies on local state encapsulation and another on well-bracketed control flow. And for future work, other than improving the lines of code, we also hope to mechanize a proof of capability safety of the awkward example, which is a particularly difficult program to reason about. And also, one of the nice things of having a mechanization, and also a very modular one, is that we can now expand the mechanization maybe a little more easily and use it as a playground to explore new capabilities that might solve certain shortcomings of older capabilities. Thank you.
Thank you for the talk. Now, have you got any questions? Sorry about that. Yeah? Mark?
So you talked a little bit about how iris is really tuned to doing higher level languages and that it can sort of undo certain abstractions, right? Go under the hood. Can you talk a little bit about that? I mean, I'm sort of wondering, does that mean you had to change iris a little, or you just had to sort of unravel definitions more?
Yeah, so this is really, it's actually right here, but it has to do with when you embed the language, iris really has this recipe in a way that it asks for. So it asks for a definition of expressions, of values, and of the operational semantics. And in our case, it was very important for us that we don't distinguish between programs and memory, because we want to have these arbitrary jumps and allow all of this expressivity. So what are expressions and what are values in our case? And it didn't really fit that question. So instead we have this notion of abstract instructions, where our expressions are just flags that say how to interpret memory. And then the program lies entirely in memory as ghost state. So I think what it ends up looking like in the program logic is that everything is in the pre and post condition, like the program is in the pre and post condition, and then in the middle, what typically has the program is now just a flag that says how to interpret memory.
We have time for one more. Deepak?
So, what internal aspect of iris do you have to expose in order to encode this public private key?
Well, so there's a lot to answer in that, I think. But we for example had to have a resource algebra to describe the state transition systems.
But that already exists in iris, right? I mean, it's a standard thing, right?
Yeah, that's a separate thing. I mean,
yeah,
of course, that's not really exposing anything from iris, but it is pulling out what iris typically abstracts away.
Sure. Okay, I see. Okay.
All right. Thank you.